Welcome back to our another video on exploration of the Nile River's annual streamflow data using time series analysis. The data we're looking at spans from 1871 to 1970, offering a rich context for understanding the river's flow patterns over time. We will employ ARIMA models, a popular choice for time series forecasting, to analyze this data. The process involves identifying the optimal parameters for our model, fitting the model to the data, and then generating forecasts. By comparing different ARIMA models, we aim to select the one that best fits our data and provides the most accurate forecasts. Let's start with an introduction. We will use the famous Nile River's annual streamflow data, conveniently stored in a time series dataset named Nile. This dataset goes beyond just numbers, it also includes metadata, providing valuable context. When you call print function, you'll see details like start equals 1871, indicating the first year of data collection, and end equals 1970, marking the final year covered in this specific dataset. To make sure the Nile is a time series data, you can use is.ts and plas function to verify this. The plot function visualizes the historical flow patterns of data. We can observe variations in flow throughout the years, potentially indicating trends or long-term changes. Now, let's move on to model identification. We shall use the two most commonly used functions, ACF and pacf, to analyze the time series properties of this data. Based on the autocorrelation plot in the image, it appears that an ARIMA order of 1, 1, 0 might be appropriate. This is because the ACF plot shows a single spike at lag 1, and then dies off afterwards. This suggests that there is an autoregressive term of order 1, AR1, in the model, but no higher order terms are needed. Further, we can also see that the autocorrelation values also do not come to zero reasonably quickly, indicates no stationarity and the series need to be differenced. The ACF plot also shows some spikes that cut off after a few lags, but they are not as clear-cut as the pacf plot. This further suggests that a moving average term, MA, is not required in the model. There is no evidence in the plots to suggest that a seasonal component should be included in the model. The pacf and ACF plots do not exhibit any periodic patterns, which would be indicative of a seasonal component. Based on these facts, we will select ARIMA model of order 1, 1, 0. Let's use the auto.arima function to identify the optimal order for ARIMA model for this time series data. This function will automatically search for the best combination of parameters, P, D, Q, based on statistical criteria. While auto.arima suggests ARIMA 111, it's wise to compare it to ARIMA 110 from the ACF plot and ARIMA 100 with no differencing. This will ensure to select the best possible model by comparing their characteristics. We can use statistical tests like AIC or BIC to see which model achieves a better fit for this data. Both the AIC and BIC values for AutoFit model are lower than the corresponding values for ARFit and ArdFit models. Generally, lower AIC and BIC indicate a better fit for the data. While the difference in AIC between AutoFit and ArdFit is relatively small, around 14, it still suggests a slight preference for AutoFit. BIC also favors AutoFit with a clearer margin. Given that the ARIMA 111 model demonstrated a better fit compared to the other two models, we can proceed with generating 10-step forecasts using this model. It's important to remember that these forecasts are based on the assumption that the underlying patterns in the data will continue to hold for the forecasted period. While the ARIMA 111 model will be our primary forecast due to its superior fit, it can also be informative to generate forecasts for the other two models. This comparison can help us visualize the potential range of future values and assess the confidence level in our primary forecast. This code block generates three visualizations comparing the forecasted Nile River streamflow using different ARIMA models. The par line sets up a grid layout with 3 rows and 1 column to display the plots efficiently. The ts.plot function line displays the actual Nile River streamflow data along with a time axis limited to the years 1871 to 1980. The points function plots the predicted streamflow values as a red line. Here are some observations based on the above predictions. AutoFit model provided relatively small prediction ranges and standard errors compared to the other two models, indicating potentially more precise predictions. ARFit model has larger prediction ranges but still reasonable standard errors, suggesting moderate precision. ARD-fit model has the smallest prediction range but also the largest standard errors, indicating potentially less reliable predictions due to higher uncertainty. This analysis underscores the importance of model selection in time series forecasting and the value of comparing different models to ensure the best possible predictions. Thank you for joining us in this exploration of time series analysis using ARIMA models. We hope you found it informative and helpful. Stay tuned for more such analyses in the future. See you in the next video.